Okay, so while you're doing that, on Wednesday we finished up twinning and starting to talk about Martensite, and we mentioned that they're a lot in common, right? They're both a shear transformation. The primary difference is, of course, Martensite is a phase transformation, so your crystal structure isn't the same after your transformation. And we talked about the Bain distortion as an example in steel, how you can go from a FCC to a BCC lattice. At first, you can imagine that the FCC is actually a special case of the BCT lattice, body-centered tetragonal lattice. And by doing compression along the C-axis and simultaneous expansion along the A-axis, you can end up with a BCC unit cell. The problem with the Bain distortions is they don't actually predict the correct orientation relationships, and the Bain distortion doesn't give you an invariant plane, the habit plane of the Martensite. So we need to go to what we said was the phenomenological theory of Martensite, right? And this is basically this slide, right? Which basically said the phenomenological theory says we can envision the transformation of Martensite as a set of three processes, right? And this is, keep in mind, this is a model of how Martensite is formed, right? It's not the actual process. You don't actually have the Bain distortion and then a shear and then a rotation, right? This is a model that aids in our understanding, that captures a lot of the features, right? And so we talked about we have the Bain distortion, a shear transformation, which then maintains the lattice symmetry and gives us our undistorted plane, but the undistorted plane lies in the wrong orientation, so then we need a rigid body rotation to bring that into position, right? And this is the key idea to know. In the notes and in the reading, there's a whole lot about the geometry of this, and that's for your information only, right? That's not examinable material, right? And then we said that we have this shear, right? We have this arbitrary shearing process that we need during this second step. And there's two ways we can accommodate this shear, either by slip on many parallel slip systems, in which case then we have slipped Martensite, or, right, and we do see experimental evidence of that, or through a series of twins, in which case we have twin Martensite, and of course the amount of shear of the twin is not exactly the same as the amount of shear that we need for the Martensite to get the invariant plane. So you actually have to have two variants of the twins that when you superpose their shear together in the right combination, you get the overall shear that you need. Right? And this is sort of exactly what we see. And I said the major successes of this phenomenological theory of Martensite is that it explained the existence of irrational habit planes. In contrast, well, we say in deformation twins, the habit plane is typically rational, but we get irrational habit planes which are different than those are predicted by the analysis that was done by Kurjamov-Sachs or Nishiyama-Wasserman. We see the in-between planes, the Grenier-Troiano type orientation relationships. Right? But as I also said, that in real steels, there's a lot of variability of the habit plane, right? It's a strong function of the carbon concentration. It's also going to be a function of the elastic strain. So there's a huge amount of scatter. If you measure the orientation relationships in Martensite from the same sample, you get a very wide distribution, right? And this was all predicted by the phenomenological theory. And before it was observed microscopically, it predicted that we're going to need this fine structure, either the slip or the twinning, right? So again, it's pretty awesome that someone was able to come up with a crystallographic theory that made predictions that was then able to be observed. It's not often modeling and theory, theoretical work you get to actually do that, right? And then I think is the last thing I said right as my computer died was that that there's a critical carbon content, and as you change the carbon content, you move from habit planes that are near 111 to those that are near 225, and then eventually as you increase the carbon content, you end up with habit planes that are near 259, right? Right, and you also move from generally slipped Martensite to twin Martensite with increase of the carbon content, right? And so we see again, just for information, right here we see what's the experimentally observed orientation relationships and habit planes and the structure of the Martensite for different systems, right? And so you can see carbon and nickel have huge effects on the structure and the kinetics of the Martensite. Okay. So as I said before, Martensite is largely athermal, right? The transformation is not time dependent. It's only temperature dependent, right? Provided you're fast enough to miss the nose of the cooling curves of your other phases, if you hit the Martensite start temperature before anything else happens, it doesn't really matter how slowly you cool down through the Martensite regime, as long as you cool through the Martensite finish temperature, right? So, this is just an example. This is indium thallium, which is actually a shape memory alloy. This is one of those archetypical alloys that's used for studying Martensite, not because it has any practical application. It's just that the shear is very small so that you don't have accompanying plastic deformation, right? And it's highly reversible because the shear and rotation is very small. And it goes from a cubic to tetragonal, right? And this just shows essentially the Martensite start, the Martensite finish. In this case, it transforms over a very small range, but we do see hysteresis, right? On cooling, right, we don't start transforming Martensite, forming Martensite till about, let's say, 344, right? And then by 338, we're essentially completely Martensite. And then as we heat, we stay Martensitic.
What is a molar?
This is that's an odd unit. It's in the reading. This should be was this done in a wire? So they just did a linear. Look at the unit length divided by the total length. Let's look in the reading and look at what it was. But
It looks like strain, but it doesn't talk.
yeah.
It just says changing length to specimen. Right.
Oh, yeah. So 1 would be the initial. The initial length. All right. But anyway, the other point I wanted to make is that if you hold at temperature, you can stabilize the interface. So here they held for a extended period of time, and you have to increase a little bit past to get the transformation to go back. But so notice this is reversible, right? This is going from austenite to martensite back to austenite in this Indian thallium system. Generally in steels, you're not reversible like this because you temper, right? You would temper the martensite out, and the carbon would diffuse, and you'd go to BCC from BCT anyway. So now you have a ferritic structure. It's not truly the BCT martensite structure anymore. Okay. Some martensitic systems do have what's called an isothermal, not isohermal, as I wrote here. Right? And basically, this says that there is a little bit of time-dependent transformation. Right? So this is an iron-nickel, and you can see you get depending on the temperature, you get a small increase after you hold it with time. Right? But notice the extent of the time-dependent nature versus the axis here, right? So if you're at 192 and you quench down to 192, you sort of instantaneously get 81% martensite, right? The athermal component. And then you go from 82 to 85, an additional 3% isothermally after a hold, right? So generally, this is not really considered a big effect, right? So in steels, something cool happens, which is this burst effect. So essentially, at temperatures slightly below martensite start, you get a large fraction that will transform in a burst, right? And again, this is something you can hear with acoustic emission, right? You actually get a propagating elastic shock wave through your material that you can pick up acoustically, right? And essentially, it's an autocatalytic effect, right? So it's a self-accelerating effect, like a nuclear explosion, right? You have a couple fission reactions, and those products go out and trigger a whole bunch of others, in which case you get a couple plates that form, right? And then you have other plates that nucleate from that plate once it reaches a grain boundary or intersects another, right? And you get these burst type phenomena, right? And this happens very, very quickly after you cool down past the martensite start temperature, right? So if you remember back, the steel I'm talking about a slightly different topic here. I'm going to get to that in just a second. right? So all iron steel martensites have very large dislocation densities, right? As I said before, the low carbon steels are mostly dislocation. High carbon are twinned, but they all have very large dislocation densities. So why would a twinned martensite structure still have a very large dislocation density? What was the approximate shear for iron carb for steel for the martensite? What was if you go back to the very beginning, we said we had the invariant shear was about 20%, then another 10% dilatational or normal strain. It's a large amount of shear that needs to be accommodated by plastic deformation in the austenite, right? Those dislocations don't just necessarily go anywhere, right? So you've got plastic deformation happening in your whole structure that those dislocations are still there after the shear, right? And so about 4 years ago, is anyone with Pete's group still doing the crystal plasticity martensite CPFE work? No. Anyway, Professor Anderson did some really nice work with that, looking at the localization of plasticity that's associated with the martensite transformation, right? That's Pete. Right? He picks up a cool topic and then runs in different directions. I always thought that was something. There's really a lot of depth that could go on there. Okay. Nucleation of martensite. So I said nucleation of twins was a controversial area, right? And there's a whole bunch of mechanisms, and people get into horrible fights about them. Martensite's even worse. There are tons of theories. None of them are really any good, right? There's no clear winner. We have a fact that we do have that whatever theory would need to explain both the athermal, which happens in a fraction of a second, or the isothermal component, which needs a finite amount of time. There are I sort of generally broke the theories down into these coherent nuclei that form purely by shear, dislocation-mediated nucleation mechanisms, and then strain energy-mediated nucleation mechanisms are sort of the three big families. If you have a copy of Porter and Easterling, right, you can read, there's a whole chapter in there that covers all of these different mechanisms in great detail. But for the purposes of this class, I don't think it matters very much, right? We just don't know, and it has no technical importance, right? Growth, on the other hand, right, is we know for a fact that thermal activation is not a factor for growth, right? So plates grow to their final size with very great rapidity. Once you nucleate the martensite, you have a plate. Right? Essentially, it translates at the shear wave velocity, close to the shear wave velocity in the material. So approximately that of the speed of sound is the rate of growth for martensite, right? So much, much faster than any thermally activated process, and that as far as we can measure, the growth velocity is independent of temperature, right? So this basically just says this is not at all consistent with any thermally activated process for growth, because if that was the case, there would be a temperature dependence, right? Even if it was only a short-range atomic jumps that you had to account for. So even at liquid helium temperatures, we observe the same kinetics, essentially, for Martensite growth as at higher temperatures, right? So growth is a completely an athermal process. But there may be, well, we know there is a small thermal component to, a isothermal component to nucleation. What that is, we really don't know. Right? It's kind of humbling to say, like, these are really classical metallurgy problems that we still don't know the answer to. Right? It's humbling on one side because, man, we should have figured this out right now, right? By now, right? Everyone, for what we use steel for, we should be better at it. On the other hand, it's exciting because it means that there's still lots of cool problems to go after, right? Okay. So, yeah. Twinning growth is not well, in deformation twinning, it's a dislocation mediated process, right? So you need either the stress to move the twinning partial dislocations along the interface to move it, right? So it's not purely a I guess sort of the equivalent would be if deformation twinning was independent of the applied stress, right? Right, it would happen at the growth kinetics would be the same at a stress just a little bit above the critical resolved shear stress, we'll say. I don't believe that there actually is a critically resolved shear stress for twinning, but just above that, or 10 times as large, that the twin growth rate would be the same. Here we're saying you just need, as soon as whether you have a huge amount of driving force, whether you're really below the Martensite start or you're just a little below the Martensite start, the growth kinetics are the same, right? I guess that's would be the analogy that I would make with twinning there. Okay. But we can have stress-induced Martensite as well in certain systems, right? This is the essentially the shape memory alloys, right? So in SMAs, you have the pseudoelastic effect and the shape memory effect, right? The pseudoelastic effect, right? You have austenite to martensite, right? A stress-induced phase transformation. Right? That's fully recoverable, right? So in this case, copper zinc SMA, right? You can get essentially an 8% fully recoverable strain, right? But it's not truly elastic, right? We say pseudoelastic because that transformation is really the shear of the martensite, right? So you notice that once the transformation really starts, your stress doesn't increase. Once you're at the end of your transformation, your stress starts to go up. If you continued to pull this, it would deform plastically and break very quickly because the martensite doesn't have a lot of ductility, right? If you pulled it any more than this just so it started to yield, you would not get full recovery, right? So there's a limit to the pseudoelastic effect, right? Once everything's completely martensitic, bad things happen, right? So, right. And so it also only sort of works over a certain temperature range, right? So this is sort of the temperature dependence of the stress needed to activate the pseudoelastic effect, right? So at higher temperatures, you need higher stresses, right?
What is the reason for this?
For this hysteresis, right? I mean, it's just the work done during the process, right? You have all your inefficiencies, right? If you had a perfect single crystal, right, and you were just transforming it there and back, your hysteresis would be very small, if measurable at all. But here you still have a polycrystal, right? So not all of your variants are perfectly aligned with your direction, right? So you still have localized plasticity and other things happening, right? It is reversible on the micro scale, right? There's anelasticity here, right? But on the very locally scale, it's not completely reversible everywhere, right? And if you cycle this many times, the amount of recoverable strain decreases with the number of cycles, right? When right, the counter to that is the sort of the shape memory the shape memory effect, right? Right, where you can use the strain from the shape memory effect to do useful work, right? And the amount of useful work you can do decreases with multiple cycles for the same reason, right? So I guess before I get into that, I need to explain what the SMA shape memory effect is for for everyone else who's not working in it. So everyone knows, like, nitinol wire, right? Right? You've got some shape, you crumple it into a ball, you throw it into a hot cup of coffee, and it magically returns to its original shape, right? So that's one effect. This pseudoelastic effect is what, those shape memory eyeglasses. I used to have a pair, right? You could bend them and they would instantaneously pop back, right? That was this pseudoelastic SMA effect. The shape memory, on the other hand, right? So if we work around the right, we have a shape that's austenite, then we rapidly quench it, we get a Martensitic transformation on cooling, and provided we keep it fixed in shape, right? We don't have a shape change, right? And then essentially we can deform, and we have, if we're below the MF temperature, we can deform it, and we get variant coalescence on stressing, right? When we deform, we accommodate the strain by transforming from one variant to the other, right? So we're accommodating that shear by phase transformation rather than by plasticity, right? Then when we heat it back up, we recover the original shape as we go back to the austenite phase, right? Then when we cool back down, it goes to Martensite again and stays in that original that original shape, right? And so this is used a lot for actuators and in biomedical applications, right? You can have biocompatible shape memory alloys that are used as arterial stents, right? They can be small, right? You set them at their full diameter. It's like a little cage. Looks like a big carbon nanotube, right? It's this truss of very fine wire that is set at some diameter. And then when the surgeon wants to pull it in, you can essentially pull it like one of those Chinese finger traps, and it gets smaller, and it stays that way. Then it's rapidly inserted into the vein that it needs to, or artery that it needs to hold open, and under the body temperature, the shape memory effect kicks in, and it goes back to its full size and maintains the pressure of the thing. It's also used. Boeing uses them as actuators, potentially under thermal conditions, right? So I don't know if it ever made it into a plane, but there was a design where, with like the masks that fall down, those were essentially a shape memory actuated thing, because you don't want anyone opening that during the flight, right? So you need it to be maintained. But basically, when they turned on a switch, a small current passed through. The shape memory heated up from the actuator heats up from Joule effect and contracts, and all of a sudden the latch opens and all the oxygen masks fall down, right? And it's a sort of resettable, tamper-proof system that could be used. There's other places within the engine, right? In the turbine engine where you want, you can imagine where you want temperature-dependent actuation, right, over a very narrow range to a very high degree of controlled strain, right? And SMAs are useful in some of those applications. Okay. So this is basically saying the same thing as I said before. At low carbon steels, we have a Kurgyumov-Sachs type orientation relationship, and we get a laugh or slipped type Martensite with a habit plane close to 111. As we increase, we have an increased carbon content. Our Martensite start temperature decreases, right? And we transform from a slip Martensite to a twin Martensite. And at high carbons, we're very heavily twinned. We have lenticular plates rather than needle-like laths. And we've transitioned to near this Nishiyama-Wassermann orientation relationship. Right? So nothing that I hadn't said before, but it's just kind of graphically showing the effect of carbon and alloying on the Martensite start temperature. Right? Other alloying elements can have a fairly pronounced effect, and essentially what you do is you can convert different alloying compounds to an effective carbon content, right? And so then you can write a relationship that gives you an approximate Martensite start based on the composition. Carbon is the most effective alloying element at depressing the Martensite start. So this relationship is highly empirical and highly approximate, and it's not really used these types of things, except outside of like teaching anymore, right? If you were actually thermocalc modeling is much more accurate for predicting Martensite than these types of relationships. Right? Okay.
So why is increasing the carbon decrease the MS?
Because there isn't room. It wants to go to ferrite, right? There isn't room, so that's why it's tetragonal, right? Because the huge distortion that the carbon atom makes. If you have more carbon in there, you're going to have much more distortion in your Martensite structure, right? So the energy associated with that distortion keeps it as stabilizes the austenite for lower temperatures. Right? Does that make sense? Right. The more carbon you have, the more heavily distorted your structure is going to be. Okay. Yeah.
When you have 0.3% carbon, why do you still have a Martensite start?
Because you can have Martensite forms in other systems like iron nickel. So with other alloying elements, you can have nominally a steel composition, right? And then keep everything else fixed and remove the Martensite, remove the carbon. It's arguable when you get down to it, right? Are you still a steel? Most people would kind of say yes, right? Because you started your alloy as an iron carbon, right? But you can have steels with 0.8% carbon, right? If you go back to the definition of steel I gave at the very beginning was alloys that started their development around the iron carbon eutectoid idea, right? But just because it started there doesn't necessarily mean it ended up there. Right? So Mar-aging steels, for example, right? Yeah.
Pure iron can have
No. In what I'm saying is that if you have like an iron nickel system, you can have compositions in pure iron. I don't know. You might be able to have iron in Martensite and pure iron if you cool it fast enough, right? If you get down, right? If you can cool it more quickly than the massive transformation, right? For austenite to ferrite, then you could. So it wouldn't surprise me if it's been reported, but right. Theoretically, yes. I don't know if it actually exists. It has? Okay. So, yes. I had to think about that for a second. But yeah, there's no reason why you couldn't. It'd be analogous to you can get alpha to beta titanium, right? Either diffusionally or Martensite, depending on your speed, right? So here we have iron nickel carbon, and it's just comparing the hardness as a proxy for strength this is iron carbon alloys where you have Martensite with the addition of nickel where you stabilize the austenite. And so as a function, the strength as a function of percent carbon, and you can see that the Martensite has a huge role in the strength, right? the fine lath structure and the BCT structure gives you very, very, very high strengths, but very small ductility, right? Purely martensitic steel is very brittle. And also the strength does increase a little bit with aging, right? As you get some diffusion at room temperature to the grain boundaries, right? So sort of like a auto tempering is not really the right word, but because you're not diffusing out all the carbon and leaving ferrite, but you do get some motion to the interface. Okay? And so a lot of this lath and twin martensite gives you a slight difference in strength, but it's not really all that significant. And this is a Hall-Petch type effect as a function of the lath thickness. So the fineness of your martensite structure also is going to affect your strengthening, right? So that's it on twinning and martensite.